Hello, welcome to the video of methods of detecting exoplanets, gravitational microlensing. In this video, I'll be discussing how you go about using the gravitational microlensing curves and how they are used to display or allow astronomers to know about the presence of an exoplanet. Okay. So before we actually begin, one thing that you have to remember with gravitational microlensing, what is actually causing it? And if you remember, of course, we talked about Einstein's theory of general relativity, and general relativity focuses on gravity being a result of really the curvature of space-time. And so what you see here is you see Earth actually curving space-time its actual self. And this curvature is what the actual moon follows in its orbit around Earth. So whenever you start understanding about how this is actually used, what you're going to notice is that this curvature is going to actually have an influence on light. And so as you can see here, imagine looking at a distant star. So we're looking at this star that is way up here, and then all of a sudden the sun, let's just say the sun moves across in front of it, and now you notice that the sun has curved this space-time, and so the light is actually going to be bent off of that. And so this concept allows astronomers to detect exoplanets, okay, and their orbits around the stars. So what ends up happening is as you have this star, the foreground star with the exoplanet move in front of that background star, you're going to be, the light's going to be deflected inwards, and you can see that it actually looks a lot brighter. Now, you could see things like Einstein rings. There's all sorts of different things that you can actually see that's caused by this distortion of space-time around this object. But the thing is like, how does this actually work? So, as you start out here, what you see is you see light from a distant star actually coming towards Earth, which is the blue dot at the bottom. And now we have an exoplanet, or excuse me, we have another star that has an exoplanet around it. Well, let's just look at this actual other star passing in front of the star that we were previously looking at. You notice how it starts to bend the light rays, and that's because of that curvature of space. And as it continues on, you can see how it's distorting the actual space-time around it. And now what it's doing is it's intensifying the light from that distant star because the curvature of space is concentrating it towards Earth. And that right there is what is called gravitational microlensing. And then as it continues to move out, you end up seeing that the distortion of space and the light returns to its normal pathways coming towards Earth. Well, what do astronomers do? They end up analyzing this light, and what you can actually see is you can see that this is generated a brightness curve. Okay? Now, here's the thing. If you look up here, this is where a lot of confusion starts to arise, because it's like, okay, how is the graph actually recorded? Do you focus it on the recording aspect, or do you focus it on the graph aspect? So before we do this, here's what you've got to look at. Here's our scenario. We have an exoplanet orbiting a star, and the Earth is viewing this distant star. So astronomers here on Earth are viewing this star. And so what you do is you interpret the graph. So as you come across in time, so you're increasing in time, what's the first object that's going to pass in front of this actual distant star? Well, that's going to be the exoplanet. And that's why you see this change in the light curve. Now, here's the thing about this light curve, what it can actually do right there. That's the presence of the exoplanet. So because it came through first, that means that the exoplanet was the first thing through. This curve is actually the star coming through. Okay? So what you have to do is you have to remember this is going through time. So you just simply interpret the graph. Nothing in front, and then curvature of space starts to distort that, and then there's the exoplanet, and then there's the star, and now it has actually moved out of the orbit where it's deflecting any of the light between Earth and that distant star. So that's how you go ahead and interpret that. Now, here's some key things that you want to look at. Notice the spacing. The spacing that you have here, that is a good indication of mass. The more mass that an object has, the more distortion that's going to occur, right? And so what that's going to do, by looking at this thickness, you're basically, or how wide this is, I should more accurately say, how wide this is, that's going to give you a good indication of mass. So this is indicating to me that you actually have a kind of high mass exoplanet. So this could be something like a gas giant exoplanet, a hot Jupiter, several different of those higher mass objects, super Earths, that can actually cause this. If you see a really, really thin one though, the distance between this is very short, that's an indication of a low mass, like a terrestrial type of exoplanet. Okay? All right, so let's go ahead and see what we actually have here and watch how this actually occurs. Okay, so we've got the exoplanet and star system here. You can see it's moving up. It's not really moving, it's just kind of getting into position now. And now you're going to start to see this is what the light's going to happen, but focus on the left-hand side. So what you see there is you saw the one graph, see how thin it is, and then the bigger graph. That indicates to me that the exoplanet, as you can see on the right, was the first thing actually through. And so what that ends up doing is by looking at that light curve, if it were just a star, you would just see one big curve. But because you see that extra dip in there, that is actually indication of an exoplanet being present. And that's how astronomers can use gravitational microlensing to actually locate exoplanets. So, looking at this, let's look at this planetary system. And then it's going to be passing in front of the orange distant star. Which of these graphs would you actually pick to best represent this scenario? Go ahead and pause the video, think about it, and you'll come back with your answer. Okay, from that, what you should have actually chosen is whenever you look at this, you have a small mass exoplanet and a large mass exoplanet. Okay, and so by looking at this, you're looking for something that is probably relatively thin first. So you have the small exoplanet first, and then you have the larger exoplanet last. And so by looking at these actual conditions, let's go to each graph. This one you say, okay, I come up, that's kind of thin right there. And then you're saying, okay, here's the problem though. Notice the distance between those two. They should be really close together. This is much farther apart. This is much closer together. So it is definitely not A. This here, you start to go up and you notice that, okay, I've got a wide base there, so that would be the large exoplanet first. That's actually incorrect. Plus, notice how close that they actually are. Okay, this, you've got the small exoplanet, then the star, and notice how far away this is. That right there. So now we figured out a different thing. We figured out that, wow, wait a second, the distance between the star and this is an indication of the orbital distance of that exoplanet. So letter C is actually the correct answer. So hopefully this video does a good job of explaining how gravitational microlensing actually occurs. There's always some confusion on, it depends on how you perceive the graph. Is it being perceived from, do you read it from over here? Or how do you do it? And the answer is no. You start at 0, you read, and you say, okay, there's the first object through, there's my star, there's another exoplanet in this condition. Okay, so again, C is the actual answer here, so you can use this to help you complete any of the assignments that we have on exoplanet detection.